All right, welcome back for example 2. Before we get started with example 2, we got to talk about a few theorems dealing with rhombuses. So, with rhombuses, one states that if one pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. So we're trying to determine whether figures are rhombuses or not. So the key thing is if one pair of consecutive sides of a parallelogram. So we first need to know that it's a parallelogram, right? Then it says if one pair of consecutive sides, what are consecutive sides? Consecutive sides are sides that are right next to each other. So like here, EF and EH, those are consecutive sides. They're sides that are right next to each other. So what it's saying is if these two are congruent of a parallelogram, right? We have two sets of parallel sides. So we know that this is a parallelogram. And if two consecutive sides are congruent, then the parallelogram is a rhombus. So a parallelogram with one pair of consecutive sides congruent, then it is a rhombus. So, consecutive sides could be this side and this side, or this side and this side are consecutive, or this side and this side. You just need one pair of consecutive sides to be congruent for it to be a rhombus. And why is that? Think about it, right? If we know it's a parallelogram, what do we know about a parallelogram? Opposite sides are congruent. So if this side is congruent, this side, it's a parallelogram, so these are the same. And then these would be the same, right? Because opposite sides are congruent. And then you see every single side is the same length. So, so all you need to know, if it's a parallelogram, is that two consecutive sides are congruent. Then it is a rhombus. Okay, so that's the first one. Let's go ahead and look at the next. The next one states, if the diagonals of a parallelogram are perpendicular. So we need a parallelogram again, okay? This idea of a parallelogram is super important. So if the diagonals, so we're talking about the diagonals, of a parallelogram are perpendicular, then the parallelogram is a rhombus. And okay, so a parallelogram with diagonals perpendicular, it's a rhombus. Okay, so we have two sets of sides that are parallel, right? And here are our diagonals, and our diagonal is perpendicular, so we know it is a rhombus. Okay. Let's look at the next one here, which states if one diagonal of a parallelogram, okay, so we have to have a parallelogram again, okay? If one diagonal of a parallelogram bisects a pair of opposite angles. So if one diagonal of a parallelogram bisects, means cuts in half, a pair of opposite angles, then the parallelogram is a rhombus. So if a parallelogram with diagonals bisecting opposite angles, then it is a rhombus. So we have two sets of parallel sides, so we know it's a parallelogram. And if we look here, this diagonal is bisected. It makes these the same, and it makes these the same. That means it bisects, right? So we know that if this diagonal bisects one pair of opposite angles, then it is a rhombus. Okay? So those are the three theorems that let you know whether it is a rhombus. So super important right here, in order to apply these theorems, right, these two for rectangles and these three for rhombuses, the quadrilateral must be a what? It's got to be a parallelogram. Parallelogram, 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 and these are the ones for rectangles. Parallelogram, parallelogram. It's got to be a parallelogram, okay? So in order to apply those 5 theorems, the quadrilateral must be a parallelogram, okay? And furthermore, to prove that a quadrilateral, right, 4-sided figure is a square, it is sufficient to show that the figure is both a rectangle and a rhombus, and to prove that it's a rectangle and a rhombus, you have to know it is a parallelogram, right? So if you start with a quadrilateral, the first thing you have to do is prove that it's a parallelogram. then prove that it's a rectangle, then prove that it's a rhombus to prove that it's a square, okay? So to prove that a given quadrilateral is a square, so whenever you're trying to prove that it's a square, it is sufficient to show that the figure is both a rectangle and rhombus. So let's just state this. To prove it's a square, it's a square, okay? To prove it's a square, you have to first prove it is a parallelogram, and then you have to prove it is a rectangle, and then you have to prove it is a rhombus, and if all of those things, then it is a square. That is how you prove that it's a square. So there's no more additional theorems to prove that it's a square. You just have to prove it's a parallelogram, rectangle, and rhombus, and that's a square. And think about it, right? Rhombuses, all the sides are the same. What do we know about square? All the sides are the same, and all of the angles are 90 degrees, right? So a rhombus, all the sides are the same, and an angle has that 90 degree in each angle, so that's why you know it's a square. Okay, perfect. Okay, let's go ahead and look at a few examples. We're going to be appreciating examples, so get ready to appreciate. All right. So looking at 2A first. Okay, I'm just going to cover up this answer briefly. Okay, and please don't look ahead at the answer. Example 2A, it says applying conditions for special parallelograms. So determine if the conclusion is valid. If not, tell what additional information is needed to make it valid. So given, what are we given? We're given that EF is congruent to FG. So EF is congruent to FG. Ooh, what does that look like? Does that look like consecutive sides, right? Consecutive sides. So if this consecutive sides are congruent, we would know that it is a rhombus, but there's something else about that rhombus. What do we need to know for a rhombus in order to know it's a rhombus, right? Okay, so consecutive sides there, that's nice. It looks like we're going in the right direction. What's the other thing? EG and FJ is perpendicular to FH. So EG and FH is perpendicular. Oh, that's good too. So let's look here, and we have to, the conclusion is EFGH is a rhombus. So that's what we're trying to prove, right? So can we do that? Is there enough information to prove that? Well, let's first look at this consecutive side theorem. It says if one pair of consecutive sides of a parallelogram, oh, do we have a parallelogram? Do we have any information that we can say that it's a parallelogram? We do not at this point. So even though we have that consecutive side information, which is lovely, if one pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. We have the consecutive sides, but we don't have that it's a parallelogram, so we can't use this theorem. Okay, well, let's look at the next one. It says if the diagonals of a parallelogram are perpendicular. Do we have that? Yes, we have diagonals that are perpendicular, but do we have diagonals of a parallelogram? We do not have information that states that this is a parallelogram. So even though these two pieces of information are so close to proving that it's a rhombus, we do not have the fact that it is a parallelogram, so those theorems do not help us. They only help us if it is a parallelogram. So, to apply, so the conclusion is not valid, right? The conclusion is not valid by the theorem 653, which is this lovely theorem here, 653. If one pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. By theorem 654, which is this lovely theorem here, if the diagonals of a parallelogram are perpendicular, then the parallelogram is a rhombus. To apply either theorem you must first know that ABCD is a parallelogram, and we don't know. So the conclusion is not valid because to apply either theorem, you must first know that the ABCD is a parallelogram. Okay, so that one is not valid. All right, let's look at the next one here. Okay. I'm going to cover up the answer. Okay, I'm going to cover up like this. All right, so it says, given EB is congruent to BG, EB is congruent to BG, so EB is congruent to BG, and FB is congruent to BH. Ooh, that looks like some good information. Now, what does that tell us, right? If these are the same, these are the diagonals, right? And these are the same. This means that the diagonals bisect each other, right? So, what do you remember what we can say when the diagonals bisect each other? Think about it, think about it, think about it. And then it also says that EG, this whole diagonal, is congruent to this whole diagonal. Why would they give us that information? And then it says that triangle EBF, this triangle here, is congruent to EBH, this triangle here. I wonder why they give us that piece of information. We have to prove it is a square. Oh my goodness. Okay. Hold up. To prove it is a square, we have to prove that number one, it's a parallelogram, then it's a rectangle, then it's a rhombus, and if we can prove all three of those things, then we know it's a square. All right, so let's start with, the rectangle and the rhombus really don't matter if we can't prove that this bad boy is a parallelogram. So let's see here. How do we prove that this is a parallelogram? Well, what do we see here? We're seeing that the diagonals are bisecting each other, right? So because of this, EB is congruent to BG and FB is congruent to BH, that's the given information. We know that EFGH is a parallelogram because the quadrilateral, if you have a quadrilateral with the diagonals bisecting each other, then it is a parallelogram. So woohoo, we know that it's a parallelogram. So that's step one to proving that it is a square, right? We got to go parallelogram, rectangle, rhombus, and then if all of that is true, then we can say it's a square. So we have proven that it is a parallelogram, which is wonderful. Okay, so we use this information here, right? So now we have to prove that it's a rectangle. How would we prove that it's a rectangle? Well, if we know it's a parallelogram, and then they state what? That these diagonals are congruent, that leads to step two, to determine if it's a rectangle. So we have that we already know that it's a parallelogram, and then we have this given information that EG is congruent to FH, so that's given, and then we know it's a rectangle because EFGH is a rectangle. If you have a parallelogram with the diagonals congruent, then it is a parallelogram. Okay, so we have now that it is a rectangle. So what do we have left? A rhombus. So we've used this piece, this piece, this piece. Now they give us this. All right, so let's think about this. What are the theorems to prove that it is a rhombus? Well, all these theorems for a rhombus, you need to know it's a parallelogram. And we know it's a parallelogram, so we have access to all these, okay? The first one says one pair of consecutive sides. Okay, this says the diagonals are perpendicular, and this has a diagonal that bisects opposite angles. So when I'm looking at this, I don't see anything about these diagonals being perpendicular. And there's diagonals, but I don't really see anything about the opposite angles. We have this triangle EBF is congruent to triangle EBH. Let's go ahead and look at that really quick. So EBF is this triangle here, right? This triangle here. So it's kind of like, why would they give us this information? This is congruent to this triangle here. We know that these two triangles are congruent. Well, think about it. When we know two triangles are congruent, how many pieces of information do we know? We know six pieces. Oh, I can't get on my fingers. 6 pieces of information, right? We know that three corresponding angles are congruent, and we know that 3 corresponding sides are congruent. So what would be really convenient is if you see these are like consecutive sides, right? If these consecutive sides ended up being congruent, because we already know it's a parallelogram, right? If these consecutive sides were congruent, then we would know that this is a rhombus, right? Because if it's a parallelogram, right here, right? If it's a parallelogram with one pair of consecutive sides, then it is a rhombus. Okay, so let's see here. Let's look at this. Let's look at this right here. So this is EF. So EF is here. It's the first and the third letter, right? So that would mean EF is going to be congruent to EH. And is this EH? It is! So that means that these two sides are congruent, right? Because of, do you know? That was a really CPCTC. Okay, so let's go ahead and do it. Now, this is written incorrectly, so I am going to erase it. And you can just kind of, Okay. So the first thing we know is we know this given information, right? So we can say that triangle EBF is congruent to triangle EBH, and that is given information. And then we can say that these two sides are congruent. So EF is congruent to EH, right? Because of CPCTC, corresponding parts of congruent triangles are congruent. So then, because we know that, we can say that EFGH is a rhombus because a parallelogram with one pair of consecutive sides, a parallelogram with one pair of consecutive sides congruent, then it is a rhombus. So we have that it is now a rhombus. So because it's a parallelogram, a rectangle, and a rhombus, we need to determine that it's a square. And since EFGH is a rectangle rhombus, it has, and it's a parallelogram, right? Well, if we say it's a rectangle and a rhombus, we know that it's parallelogram. So it has 4 right angles and 4 congruent sides, so EFGH is a square by definition. The conclusion is valid, all right? So that is 2B. Let's go ahead and look at, check it out, example 2. That's a lot of work, okay? But let's just go over and just appreciate it. I mean, we're appreciating this, right? So if you have to prove that it's valid, you have to first show it's a parallelogram, then you have to show it's a rectangle, and then you have to show that it's a rhombus. And then if you show all those things, you have proven that it is a square and the conclusion is valid. All right, let's look at, check it out, example 2, right here. It's a lovely problem. And I want you to go ahead and try this one on your own. So here's my friend the pause dragon. Remind you to pause your device. Go ahead and work this out. When you get done, press play and we'll talk about it together. All right, see you in a bit. Okay, let's see how you did. This says angle ABC is a right angle. Okay, ABC. Okay, so this angle is a right angle. Conclusion, ABCD is a rectangle. What do you guys think? Well, this is good, right? Like, where is my theorem for my rectangles? Yes, what does it say? If one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. So this is great. We have one angle that is a right angle, but do we have that it's a parallelogram? Do we have that it states a parallelogram, or do we have the information, given information that lets us know this is a parallelogram? And no, we don't. It is so heartbreaking. We're so close, but so far. So the conclusion is not valid because we do not know if A, B, C, D is a parallelogram. All right, if you got that one right, woohoo, you did wonderful. That's it for example 2. I'll see you in a little bit for example 3.